Alright, everybody, or I guess right now it's just mommy, but I don't know, in the future maybe it will be more people. Today I'm just going to be covering dynamic programming, what it's about, um, what its use cases, and I'm just going to demonstrate a simple example of how it's typically used. So, to understand dynamic programming, you first have to understand the concept of recursion. We could go through a very quick example of recursion. A common example of a recursion problem is the Fibonacci sequence. The Fibonacci sequence is a famous mathematical expression. Essentially, it goes something like the first two numbers are 1 and then 1, and then the next number is going to be the sum of the previous two numbers, so that's going to be 2, and then the sum of these two numbers, that's going to be 3, sum of these two numbers, it's going to be 5, 8, 13, and then so on, so on. So it just keeps going like that infinitely. So our task today is to find an efficient way to solve this problem using both. First we'll go through recursion and then dynamic programming. First, for the recursion solution, what you would want to do, create a function in Python, definition of Fibonacci. We're going to take an integer as an input, so let's say int n. In Python, actually, you don't really need we don't need to specify the type, you can just say n. So now, to understand the Fibonacci code through recursion, it's basically, since we're trying to look at the first two numbers, just take the base case or the smallest specific case. So if the answer is n, you just want one number of like the Fibonacci sequence, it's only asking for one number. So let's say if n is equal to 1, what would it be? It would just return 1. It's that simple. And we also get the same thing if n is equal to 2. So we'll just say if n is equal to 2, return 1. Because both of these answers are going to return 1. If it's 1, it should return 1. If it's 2, it should also return 1. However, now the tricky part is when it gets to 2, right? So what we would do there is simply say return Fibonacci of n minus 1 plus Fibonacci of n minus 2. You can have this all in parentheses. Now essentially what that's going to do is, if for example n is equal to 3 here, what it would do is it would first compute, it wouldn't go into both of these cases, see that it's false, and then it would say, oh, let's check the number before it, which in case of 3 would just be 2, and then in the case of 1, n minus 2, which is 3 minus 2, which would be 1. Both of these would return 1, so it would return 1 and 1. And then this would just keep continuing for higher and higher numbers. Fibonacci of 3 would go into Fibonacci of 2, which goes into Fibonacci of 1 and 1. This could be represented by like a graph or something, but that would be a little bit, a lot to draw out, so I'm not going to do that. So essentially we can test if this thing works. Should have done everything right. So let's say Fibonacci of 3, and what we're expecting is for it to print out the number 2. And as we see here, it goes 2. We could test it again by saying 4. Yeah, and that's 4, so that'll return 3. 5 should return 5. And yeah, so it keeps going like that. So this is the basic recursion function of the how to solve the Fibonacci problem using basic recursion. However, the hard part of this is, the bad part of recursion is that it's going to continuously call this solution over and over. We could do like a whole time test thing, but you could kind of imagine when you're calculating Fibonacci of 13, for example, that's going to be Fibonacci 1, 2, 3, 4, 5, 6, 7. So you're trying to get to the 7th element, it would have to do Fibonacci of 6 plus Fibonacci of 5, which would be the Fibonacci of 5 plus 4 plus 3 plus 2 plus 1, and it's going to keep going like that forever and ever, and it's going to continuously do recursive calls, even when like sometimes it's like things that we've already occurred. Like for example, Fibonacci of 7 would do 6 and 5, but Fibonacci of 6 we're also calculating in a separate part, so that's just an extra step that we don't want to do. So in that case, we would do something like memoization. So to use memoization, first we would these two things could probably remain the same, but in the solution that we did, what we would do is, if Fibonacci of n is less than or equal to 1, we would just return n. Now this is because the case is a little bit different here. This is essentially the same thing as the base case. However, it's just saying that if the number is at 1 or the number is 0, we're going to be using 1 and 0 in this case, because what we're going to be doing is we're going to be using an index instead of like a normal number or number value. We're going to be using an index into an array, which the array starts at 0. So we're going to say if n is less than or equal to 1, return n. Next, we're going to be initializing the base cases in the array using memoization. So what we would do is we'd say we'll make this a list times n minus 1. So now what this is doing is, sorry, not n minus 1, it's going to be n plus 1. This is going to be creating the memoization array that we're going to be continuously storing the Fibonacci values that we've already computed into this number. So like for example, when we're computing Fibonacci of 2, we have to continuously do that over and over again dozens of times if we were to calculate a long number. So we just want to store this into an array, so we're going to call this a fib list, and in Python you can use multiplication too. I'm sure some other coding languages also have this, where you could just create an array, initialize an index, and then multiply it by a value that you want to make the list longer and stuff. Alright, so now, what do you say? What do we do next? Oh yes, we're going to do the base cases. So since we already know that the first two numbers in the list are going to be 0 and 1, right? So we're just going to set those values immediately. Fib 0 is equal to 1, and then fib of 1 is also equal to 1. So we're just going to be setting these two because we always know that the first two numbers in the Fibonacci sequence are always going to be 1. So whenever it calls the Fibonacci number, it will always refer to these numbers. Now we're going to be doing a bottom-up approach. So we're going to be taking a look at the base case and then continuously choosing the values going up. So now we're going to start from every number. This time, instead of just simply going based off of the previous two numbers like before, what we're going to be doing is creating a for loop. So for I in range, we're going to be starting with 2, and then going up to the value of n plus 1, because that's going to be the length of the memoization array we're going to do. So we're going to be looping through that list through I, and then essentially we're just going to be doing fib of I is equal to fib of I minus 1 plus fib of I minus 2. So if you notice, this is very similar to what we did in the recursive method, where instead of just adding the two numbers together, we would just be adding the previous two components of whatever number we're doing. So if we're looking for the number 3, we would be adding 2 and 1, for example. So this is what this essentially is doing, and we're doing it from the range of 2, which is after the first two ones, 2 and plus 1. So in that way, we are continuously appending these Fibonacci values that we've calculated into this memoization array, so that in the end, all we need to do is return fib of n. And now when we return this result, we are just, instead of recursively calling the same Fibonacci function over and over again, we're just going to have to be looping through this array to see if the function is already called in order to just immediately get the proper result. So since it's using a for loop, the additional time complexity is much less. The time complexity, I believe, is going to be big O of n rather than big O of 2 to the power of n in the Fibonacci sequence, because you're continuously calling the recursive function twice. So that is a significant time improvement. So now we could just do our test to make sure this is working the same as usual. Fibonacci of 5 should return us 5, since it's, I think essentially we could just fix this to be the same thing instead of just doing this thing. So yeah, now it's the 5th number, we get 1. We can test this with the base case too, just to make sure everything is alright. 1 would return 1, 2 would also return 1, 2 would also return 1, and then 3 would return 2, because 2 is the 3rd element. And yeah, it's going to continuously go up from there. So this time complexity is significantly less reduced, because instead of calling the recursive function over and over again, or instead using a loop to initialize the entire thing. Yeah, so that's pretty much it. Hopefully I explained that somewhat clearly, and yeah, I'll see if I make future videos of this. Alright then, bye.